Hello everyone, before we start I'd like to make a disclaimer. So this is not a tutorial and I'm not teaching anyone what's happening here. I'm trying to master neural nets like from scratch, and this is quite a complicated task for me because I'm a complete noob in math, and although I'm trying to learn math, not easy to learn math when you're 37 years old and you did really bad at school. But if otherwise, just using the high-level PyTorch API with all this neural net sequential, embedded layer, activation layer, hidden layer, etc., loss function, everything is defined, then the only thing that is left available to you is just using the hyperparameters. And the problem is that when the net is quite complicated and you start using the hyperparameters, you have no idea what you're doing, why exactly, etc., and try to make the net smaller. It's just three lines of code, maybe the entire net, and again, you're not very clear like what is going on, how exactly. So to make things more clear in terms of how it works internally, going for this manual matrix multiplication level is very helpful to have a sense. It's really all about the sense of how things are flowing within the net. And one of the most essential parts is the manual backpropagation. So obviously in PyTorch we have this loss.backward, which forwards the gradients through the entire architecture, like from the loss and back to the initial weights, like weights for the first layer and biases for the first layer, and weights for the second layer and biases for the second layer as well. And you don't particularly need to do this manually, but when the neural net architecture gets more complicated, for instance, if I want to go for the recurrent neural nets, then ChatGPT says there is such a thing as vanishing gradients, and obviously I can check the vanishing gradients even without like implementing my custom backward propagation by just inspecting the weight.grad attributes of the weights. But in that case, it's not really that simple to see the intermediate steps, like when we consider the first gradient of the loss, etc. So it only gives the gradients of the eventual weights and biases and not the intermediate steps for some reason, very least in my version of PyTorch. Maybe even that is not the actual case. I don't know, have this intuition, a strong feeling that I really need to go into the manual backpropagation. And the next step for me is to downgrade from PyTorch to NumPy to feel even more grounded and to try things on my own. So, what I spent the entire last night doing, I've been asking ChatGPT to give me some example feed-forward passes, and then I was manually doing the backpropagation, sending him the code, trying to check that out if I'm doing properly or not. He has been trying to explain all the math, how to take the derivatives, all this stuff, but I feel so stupid that I did realize that I need to come up with a sort of an algorithm how I can do things, how I can write the code for this backward propagation without much understanding what in particular am I doing. Yeah, but I need to make sure that the code is going to be working properly. So how can I do that? I can learn a very like strict for all life occasions algorithm, not for all life occasions, but for the all fit forward networks live occasions, no matter how many layers would be in there, and how to backpropagate through the uh, linear layers and how to backpropagate through the activation layers, like 10H in particular over in here, and how to backpropagate through the eventual loss function, which is cross entropy. So I'm focusing on not doing the regression tasks. I'm focusing at classification. And even though this is the simple XOR data set, I could have used the sigmoid instead of cross entropy. But since cross entropy allows to have multiple categories in the output classes, it's more robust, I would say. And this also works, and I would be sticking to this one just to have one loss function for all the potential tasks that I might have, because otherwise I would need to have the derivative for the sigmoid as well, which probably I could add into my list. But anyway, so um, what we're supposed to be doing in this video today, what I'm supposed to be doing, I'm going to be showcasing the way how I learn, the way how I manually do the backpropagation, like I did the whole night long last night. So eventually we will compare the gradients that has been auto backpropagated by this loss of backward. So the graph has been computed by the PyTorch internally. So we compute these values with the values that I will come up with in a manual way. So there would also be some in between, which we cannot compare with the PyTorch ones because they are not available for some reason. I have no idea why. But the eventual weights, the eventual gradients for the weights and for the biases, we can compare. And those would be the exact those gradients are the exact values that we can update the initial weights and biases by during the training process. So lots of black boxes in my current understanding, but at very least at this point I managed to make it like full grip on what's going on here. So without further ado, let me try to implement the backpropagation by hands. So to make my life a little bit easier, I provided this hints. So this gives the order in which I do the backpropagation. So we can rewrite the entire network as a single mathematical expression. And by the time I would be considering backpropagation, I would be unfolding these variables. So this can be written obviously as like half cross entropy, and then instead of L2, I can just put this expression instead of L2. Then within this expression, instead of A1, I can put this expression. Then I can strip this torch 10H, and then instead of this expression, I can put this one. So this would be one long expression. So I hope that makes sense. But no particular reason to put this on paper, on screen, because we do this backward pass, which goes like step by step, kind of recursively. You might think of this that way. And this really helps me to build the intuition of how things work. So the very first step, we need to strip the cross entropy. So we only want to extract this L2, which is these are the logits. This is the output of our net. So this is the output. So the first thing to do, we need to get the L2 gradient. So this is what I'm supposed to be doing now. So I say L2 gradient, and this is going to be equal the cross entropy gradient from the L2 itself. So I'm sending L2 as the matrix, and the batch size is how many elements I have in the batch, but in this case the batch is the whole data set, so this is like 1, 2, 3, 4 elements. So the batch size in my case is going to be 4. So L2 and the batch size of 4. Okay, so this is the first step. Then we want to unfold the L2. So L2 is this expression, and from here we can extract the weights from the second layer and the biases from the second layer. And again, all this is I just remembered this by heart, and I tried on different sets, a different number of layers, and it works all the same. So I just remember this by heart. That's it. I don't particularly understand why exactly this is done. You need to understand how derivatives work in math. I'm too stupid for that, so I just memorize things. But this is good enough, like for this kind of network. So I've memorized the fact that I can calculate the weight to gradient the following way. So I need to take the input to this expression. So to this expression, the input, this comes from the A1. So if I take the A1 transposed, yeah. So if I don't do the matrix transposition here, then the shape would not match. And just like we've seen in the previous video, when during the forward pass, if the shapes are not matching, the PyTorch would give an error. So this is needed to ensure that the matrix multiplication would actually work. So, and I need to matrix multiply this by the L2 gradient that we just calculated, right? So this was the step 2. So then the biases, and the biases, again, I just learned this by heart, and I did input this into ChatGPT like enormous number of times already. So we need to take L2 grad, and we want to sum across the axis 0, right? And want to say the keep dims equal to true. So this is just, I just remembered this. This just works, okay? Then this was step number 3. Step number 4. So we want to kind of strip weight from the second layer and biases from the second layer, because we have extracted them already. We don't need them anymore. So we have this folded A1, and we just want to unfold the A1. And here comes the activation function. So when it comes to activation functions, it gets a little bit different. So the first thing to do is to get the A1 grad and then the L1 grad. So A1 grad, A1 is what results with this function, yeah? So A1 grad, again, I have no idea why this is done this way. So if you're a smart guy in math and you know how to do these derivatives, this would probably make sense to you. So here we need to take L2 grad and multiply this by the W2 dot transpose. And this makes no sense to me at all, because when we did this, sort of clear, we have the matrix that comes from the input. So this, it comes like from the input during the feed forward. So we got this, then we input this, multiplying by ways. This makes sense. In this case, it makes no sense to me. I have no fucking idea how this works and why, but ChatGPT says that, and I get the results that do match. So again, this is just a black box, another black box that I'm using here to make it work. So I'm multiplying the L2 grad, the one we've calculated here, with the transposed weight 2. Then to get the L1 grad, so that's like unwrapping the next layer, we need to take A1 grad, the one that we've just calculated, and multiply this by the derivative of the 10H. 10H grad, and the matrix is L1. Now when we have the L1 gradient, this is very similar to like when we had the L2 gradient from doing this cross entropy gradient, and that we could get the gradient for the W2 weight for the second layer and biases for the second layer. So now we are in a very similar position, and again, if the number of layers repeats many times, these steps are always the same. So we do W1 grad. And now to find the way how to do it, I'm looking here. So first I need to find what gets as the input to the expression where it unfolds. So the expression for L1 is this one. So in this case, there was A1 that goes as an input. In this case, this is X, the initial data set that goes as an input. So here, instead of doing this A1 transposed, I do X transpose. So this is the same pattern, this one as well as this one. And I'm multiplying by L1 grad in this case, okay? And very same thing for B1 biases for the very first layer. So B1 grad equals to, again, so here we have the B2 grad. So we did summarize the L2 grad. Here we do sum on L1 grad. So L1 grad, that's sum and 0. And keep dim equals to true, and this is exactly the same thing. Okay, so we are done. Again, there might be many layers, and like the way I practice this, I just asked ChatGPT to give me this forward pass, and then I was typing this and sending to him. I was making mistakes, he was fixing all of the time. And yeah, that's the way I've been practicing this. So now I just have this feeling that whatever feed-forward network architecture I encounter, I can make this manual backward propagation like as a black box without having an understanding how exactly this happens and why. But what it gives to me, it gives to me the fact that all this in between stages, like during training, I can inspect all the in between gradients. So, like in PyTorch, yes, I could have inspect this one, and also this one and this one, but not very clear how to inspect these intermediate ones. So, just give some error. I'm not quite sure exactly why, etc. So, because I want to inspect these variables, I want to be able to know what's going on there during the training, just before they get to the very actual updatable parameters, gradients that are used as the parameters to update the actual data of the weights and biases for the first layer and for the second layer. So I can inspect that, and this gives me this feeling of like being grounded. And again, this is the intermediate step before I can go towards NumPy. So the next video, I'm going to be trying to make this exact thing, but entirely using the NumPy without any PyTorch fancy kind of stuff. And also I want to see the performance difference. NumPy is supposed to be much slower. But anyway, so let me uncomment all this stuff. Okay, this is just a typo. Hope there is no problem in math. Okay, yeah, let's have a look. So, W2grad. So this is the automatic autograd engine by PyTorch, resulting in these values. So 1386, and my manual results in 1386, which is correct. 1780, 1780, 1335, 1335. This, correct. There is a built-in torch method to compare these, and it just returns true there if they are exactly the same. But I prefer this visual kind of thing here. So B2grad, this, correct. W1grad, so the initial values, this, here, this one, here, this one, all correct. And B1grad, this, all correct. Which means that math that I did was all correct. So without particular understanding of what exactly am I doing, got the correct result. So one last thing that I wanted to tell you, maybe to inspire somebody, I don't know. Maybe there would be other stupid idiots like me who has no clue about math, but they really want to work with neural nets. So maybe if anyone like that, what I would now say would get inspiring. So I just want to show you the gap that I have in my understanding. So I have an absolutely clear understanding of what are the weights doing and what are the biases doing on each level. So when we multiply the inputs with the bias, with the weights in the first input, all this fully connected neurons, and then it gets forwarded. So after the activation function happens, it gets forwarded to the second layer, and again, all the layers are being connected. Finally, to evaluate the matter of how precisely the net the output, the end result, we use this cross entropy. So there is an error. So loss is our error, and this error means what? It means that our net is not predicting good enough, and the measure of how not good enough it predicts is this loss. But this loss is sort of an accumulated error across all the layers. So we want to know not the accumulated error from all the layers, but we want to know the errors within those variables that we can actually change to make the result better. So what can we change? We can only change these four variables. We can change the weights within the first layer weights, first layer biases, and we can also change the weights in second layer weights and the second layer biases. And the better weights and biases we have in all the layers, the less would be the eventual error. So the entire purpose of training is to find the proper values for the weights in the first layer, and the biases in the first layer, and the weights in the second layer, and the biases in the second layer. So in order to do this, we need to update all these variables by a small amount. And we need to know two things. The first thing is whether we want to make every single, so this W1, this is matrix of a shape 2, 3, yeah? So they all are matrices. So we want to update every element in the matrix. How do we want to do this? So we may either update this to the positive direction or to the negative direction. And by which amount in particular do we want to update that? So that's the core question. So if we had the value that we could update like all the corresponding values for every element in the W1. So we can update in the right direction, positive or negative, and for the right amount, by how much do we want this? Also assuming the learning rate, which is usually 0.1, and maybe any different, wherever fits best. But again, the core is like by how much and in what direction. And it's also need to swap the directions, hence we do this minus learning rate. No idea why exactly that is happening. Like you need to understand derivatives to understand that. But what I did today, this is the technique of how we can get the arrays. So wgrad is just like W array, but it contains this deltas that we need to multiply the original weights by, and assuming the learning rate and the minus learning rate, in order to update the weights slightly a little bit, so that the next time when this training loop goes further and further, every time the loss in theory should be minimized. Obviously, I don't have a training loop here in terms of the for loop, and I don't have the phase where the weights actually get updated, but I can just quickly show you this by inspecting the previous file that I created the last video. So this is the training loop. So I do the forward pass here. So the naming is a little bit different, so I'm working on the naming so that it gets more intuitive to me. So do the forward pass. Sorry, this is inference. This is training. Stupid idiot. Yeah. So I'm doing the forward pass, and I get the loss, which measures like how well my model performs. And then I reset the gradients in parameters to none. I don't need to do this in the code that I've just made because I recalculate them essentially from scratch every time there's a local variables that gets the values assigned just right within the loop. But here they are persistent. They are part of the weight. So here they need to be reset explicitly. So then once I do this loss.backward, so w1.grad gets populated with values, b1.grad gets populated with values, w2.grad populates with values, b2.grad populates with values. And then for all the parameters, so for w1, for b1, for w2, for b2, the data parameter, so there is the actual values, it gets updated by the corresponding element-wise by the corresponding grad parameter, and that's it. So over in here, I can use instead those manually calculated ones. So this gives me an option to switch to NumPy to feel more grounded, to see like if I do any error, then I'm like more in control. And yeah, and also just to make sure that in every in-between step, I may inspect how the gradients get changed, not the very like leaf elements like this weights, like not the very eventual data sets, this weights and biases, but also in between, because the graph also contains the activation functions and the loss function as well. So I can inspect those in between backpropagation gradient. And I don't know, maybe I don't really need that, but that's the way how I build my intuition about all this stuff. And when I do this, like the very last summary, that when I do this, I feel like I'm in charge, I'm in control, because when I do this high-level PyTorch API layer definition, I feel like everything just works without me, and I'm not even needed there. So that's the thing. Since I want to master this, master in terms of sense internally how this works, how this flows. Interestingly, the alternative framework is called TensorFlow, and the flow is very interesting word. It's really all about the flow. So really, like if I do this high level PyTorch API, I don't feel the flow. If I do this in the low level, even though I treat the backpropagation as black boxes, I still feel the flow. And when I feel the flow, the entire coding of this neural net makes perfect sense to me. If I don't feel the flow, it doesn't make sense to me. And yeah, I just feel like a stupid user. And here I feel like I'm a programmer, although still not all things are clear. But at the very least, downgrading. This is like neural nets are working. Like say the neural nets are learning. Say the neural net that is learning to predict the next character, the autoregressive model. So the first iterations, it just puts the spaces and the words are complete gibberish. So the word is a complete gibberish, then the space, then another word, complete gibberish. So it treats the words as sort of a black boxes. And by the time it's training, it refines the word and eventually it prints the normal words. So that's how it evolves. That's how it gets better over all of the iterations. I do exactly the same thing so that now I have this backward propagation as black boxes, and one day I will probably realize how taking derivatives actually work, and I would probably understand that. But before that, I would have an opportunity to actually practice and train myself. Because the way how the normal education is working, before you understand how you take these derivatives, you are not allowed to write some code and work with it because you are not understanding what you're doing. If I did follow that way, I would never be where I am now. Like I wrote this entire text editor. If I've been taught at the university, I would just hate coding and understand literally nothing. I would never create this text editor. I hope that something similar would happen with neural nets as well. So yeah, guys, that's it from my side. Hope that probably this has inspired somebody. So let me know in the commentaries what you think. That's it from my side. Thanks for watching and cheers.